Okay, so in order to know how the electromagnetic emission can be reduced, we need to know how a standard output driver is designed. And very often, this very simple CMOS output driver structure is we have this separate output driver where out of the core logic, we only have small gutters. There is not much fan out, so they cannot drive that much current. So we cannot directly connect the core logic to the output pin. So we need to amplify somehow the signals in order to have a good driving strength, in order to drive whatever 8 milliamps at the output. And in order to amplify that, very often it's done in a separate way where we have a small inverter, a bigger inverter, next bigger inverter, and then a very big inverter, which is then able to drive the output signal. If it's a CMOS technology, this is the worst case technology for electromagnetic emission generation. The CMOS output driver then finally might look like this. We have an N-channel transistor and a P-channel transistor. So here is the N, here is the P-channel transistor. And as we've discussed, every time we are switching, we are changing the state of the output driver. We have this crowbar current and a dynamic switching current to charge and discharge the kind of loads, especially capacitors outside. So we have this generation of noise here, 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 and here is definitely a very big generator of electromagnetic emissions. So these are the simulations. I think I've already shown you how big this crowbar current is. So we have a big current spike, so a big di over the d, and so on. And the question is now, what can be done in the output driver design in order to reduce the electromagnetic emission? And before we are answering that, I would like to ask you, what are you doing in this case to reduce the electromagnetic emission? So at least this was my job at my first company. The customer was complaining about too high electromagnetic emissions, so we already figured out it's the output driver. Then it was my job to design a new way of output driver, which has no electromagnetic emission. Noise, but where the electromagnetic emission is significantly reduced. So suppose you are now starting your career in the IC industry, your boss is complaining that the electromagnetic emission is too high. He says, yeah, we need some new ways of output drivers. Any idea what you would do? I was in the same situation, so I'm beginning also, oh, come on. So the first thing that I did, I was making a literature research in order to check what is already available on techniques to reduce the electromagnetic emission. So I was reading quite a lot of publications and papers and patents on that. And yeah, well, the basic outcome was there are mainly 3 ways we can use. We can get rid of the crowbar current. Well, this is pretty simple because why should the N-channel transistor and the P-channel transistor switch at the same time? So it's not the best way to do it. Maybe it's the fastest way to change the output from high to low, but from the EMC point of view, this is not the best way to do it. So maybe we can make a kind of so-called break before make structure so that the N-channel transistor is off when the P-channel transistor is turning on and vice versa. So this would definitely help because then there is no crowbar current anymore. Okay, any other ideas?
Slow slopes, so don't switch too fast.
Exactly. Make it as slow as possible. So why is switching fast not good? I think we already discussed it when we have this trapezoidal shaped clock signal or whatever, and we are transferring this from the time domain into the frequency domain. We can see all the harmonics up to a very high frequency range. And did I tell you the envelope function of the electromagnetic emission from a trapezoidal signal? Did we talk about that? I think, okay, then let's focus a little bit on that because I think this is quite important. So let's stay with the output driver. Let's suppose this is our output signal, as it looks like in the datasheet. As I told you, in reality, it looks a little bit different, but let's suppose this. So when we are now transferring this from the time domain into the frequency domain, So here we usually have the amplitude in dB microvolt very often. So what we can see is there is a fundamental frequency. It's the same way as we are supposing a sinusoidal signal with the fundamental switching frequency, and then we have an amplitude. So there is somewhere, let's suppose here, our fundamental frequency with a certain amplitude. And then, as we know from Jean-Baptiste Joseph Fourier, that every periodically looking signal, whatever how complicated this can be, decomposed to sinusoidal and cosinusoidal functions, which are accumulated all together to finally form this trapezoidal signal. So there will also be some kind of, well, the right way. This, so a second harmonic, and also third harmonic, and fourth harmonic, and fifth harmonic with certain amplitudes. So what we will have in the frequency range is we are having here our second harmonic, the third harmonic, the fourth harmonic, the fifth harmonic, and so on. As we discussed last time, if you have really a 50% duty cycle and the rise time and the fall time is exactly the same, we will only have the first, the third, the fifth, and so on. Sorry, I always mix odd and even up. Okay, so in total we are ending up with quite a lot of harmonics. And the interesting thing is, these harmonics, especially from this kind of trapezoidal signal, they are really going to infinity, but they are falling down with the amplitude at a certain rate. So maybe I'm not showing it that nice, but we can make a kind of envelope function, which is enveloping all these periodic peaks that we have. And there are, usually this envelope function mainly looks something like this. So there is a horizontal line, which is defined by 2 times the amplitude multiplied by, no, I have to define some things here. We have the, from here to here, sorry, the period t, and from here to here we have the high time. In our case, the high time is exactly the same as the low time if you have 50% tau. Okay, this here is then the amplitude. I hope I'm correct. This is then 2 times the amplitude tau over t. Yeah, then 20 times the logarithmic. So this is defining the value here of this horizontal line. And then we have one frequency position that is here, and another frequency position that is there, where these spectral components are falling down at a certain rate. In this range, they are falling down by minus 20 dB per decade. And here they are then falling down with additionally minus 20 dB. In total, it's then minus 40. Decade in English, minus 40 dB by English, per decade. And this frequency position here is defined by 1 over pi times the duty cycle, also the on time, the tau. And this frequency here is defined by, let's make this here, from here to here, the TR, the rise time, and let's make this here, from here to here, to TF, our fall time. And let's suppose the rise time is exactly the same as the fall time, which never ever be the case in real life, but to make it easy, rise time is equal to the fall time. Then this frequency position here is defined by 1 over pi times the rise time, or the fall time, whatever we have. Okay, and what's now the purpose for drawing this? The answer is, as Christian said, we have to switch as slow as possible. So if we are increasing the rise time and increasing the fall time to a signal that looks like this, what will happen in the frequency range? So we are not really changing the amplitude, we are not changing the ratio of this tau and t. This is exactly the same as before. So this horizontal line stays exactly the same. Also this line where it falls down by minus 20 dB stays exactly the same, but what we are changing is definitely here. We are increasing the rise time from whatever, 5 nanoseconds to 50 nanoseconds. And this will then decrease this frequency point. So it moves down to, for example, this frequency position, and then this minus 40 dB per decade declining function starts a little bit earlier, which is reducing the electromagnetic emission here in this higher frequency range. So this is very important, because if you have some electromagnetic emission problems at whatever it is, 15th harmonic or whatever, then it doesn't always make sense to play with the amplitude or the rise and fall, the duty cycle. Play with the rise time, and then you can significantly reduce the electromagnetic emission here by changing it. Okay, so and this is exactly the second thing that can be done. We can design a CMOS output driver where we can adaptively change the rise and fall time. If we need a very high-speed signal, then we can make the rise and fall time very small. But if we have to reduce the electromagnetic emission, then we can step by step increase the rise and fall time. And this is exactly what I did in my chip. Yeah, any other ideas? Rise and fall time, crowbar current. What about this dynamic switching current? So we have to charge up an external capacitor, and we have to discharge this capacitor. Well, we cannot get rid of the capacitor, this is there. Maybe we can reduce the size of the capacitor by defining that at this output only a capacitor of this value is allowed. Okay, but very often the customer wants to have some freedom, and very often they are placing a 10 nanofarad capacitor for ESD purposes. So this is a quite big capacitor. So I think the best way would be to design something internally that can handle any kind of capacitor.
Small resistance. Okay.
Yeah, but if the resistor is then there permanently, and we are driving, for example, a high signal at the output, we always have a voltage drop across the resistor, which can be a drawback because the output signal is then not 3.3 volt or 5 volt or whatever anymore. And also the heat dissipation, so the IC will definitely heat up a bit more. But resistor is the right direction. So what about placing something that gives a kind of dynamic resistor, which is adaptively at the first moment increased and then decreasing step by step until we only have the on resistance of the B channel anymore? So that we can shape somehow this dynamic current, dynamic switching current. Because if you have a resistor and there is a capacitor, we have this RC time constant is there. If we are increasing the resistor, then it takes longer until the output is reaching its final value. So we can also increase the rise and fall time by playing with the resistor. And what I did in my design, so I'll show you later, I was not placing a real resistor. I was playing with the size of the CMOS output driver, so with the B-channel transistor, for example. Okay, so we would like to have no crowbar current, so a break before make structure. What would be great if we can smooth the edges. So here in our trapezoidal signal, we have very sharp edges. And these sharp edges really result then in this declining function at minus 40 dB. If we are smoothing the edges, we are keeping the rise and fall time here in the middle part as fast as desired, but then also here smoothing it here in the final transition. We will somehow also change this point here, but it will then fall down somewhere in the range between -20 and -30 dB per decade. So it gives an additional advantage to reduce the electromagnetic emission in the high frequency range, because not so many high frequency spectral components are needed if the edges are a little bit smoother. Okay, yeah, reduce the ringing, especially the over and undershoot. As I told you, a real output signal is not looking exactly like this. It really looks like, so we have this overshoot and the undershoot, mainly coming due to the parasitic inductances in combination with the load capacitances and also parasitic capacitances. So internally there are resonant circuitries, and we are triggering then these resonant circuitries. There's all this ground bouncing that we've mentioned. So we should get rid of all this ringing, because all this ringing is also important, because this ringing also has a certain ringing frequency. And very often in the electromagnetic emission plot, you will see this ringing frequency as a kind of frequency range that is extending out of the typical trapezoidal switching signals. So we can reduce these ringing frequencies. And this can be done by an active control of the resistance. Now we are here at the resistance. Yeah, moderate the dynamic switching current. So instead of having a big di over dt current spike, we would like to have a very smooth transition of the di over dt current spike in order to charge and discharge this external capacitor. And if possible, we can also do something in order to change the slew rate, so that if needed, we have a very fast transition, but if not, we can switch it a little bit. Yeah, and if possible, this should be done digitally, because we are controlling everything from the core logic. Yeah, in order to do that, this was then the outcome of my literature research. There are three main techniques. One is based on the so-called distributed and weighted technique, as you can see here. Then a feedback technique and a digitally controlled technique. Distributed and weighted means that I'm not using a big P channel and a big N channel transistor as a final stage, and I'm turning this one on or this one on. I'm splitting this big P and N channel transistor in several parts. A smaller one, a bigger one, next bigger one, and a very big one. This is this weighted, and distributed means that I'm turning them on in a very special order. So I'm not turning on all these transistors at the same time. I'm turning on a small one, then a bigger one. Okay, we're coming to that anyway. Then feedback is done by a kind of feedback loop. I'm checking how far is the output signal already raised, and I'm using this information to change the driving strengths of my CMOS P and N channel transistor. And the last one is a kind of digitally controlled, where I also have different output driver strengths and also with a feedback loop. So this is, compared to the other ones, pretty complicated and not that often used. So in my output driver that I have designed, I have then finally focused on the distributed and weighted technique. Why? Because on the one hand, it's very simple, and on the other hand, I do not have that much feedback. Although feedback would be highly appreciated, because then I can really control my output signal no matter what kind of capacitor or output load I have. But what could be a drawback related to feedbacks? So where I have a direct connection from the output signal to my internal control structure. A couple of minutes ago, we have talked about RF interference, where we are injecting some signals into an IC. And these feedback structures, they very often have the problem that if this is my output, there is then a printed circuit board connected or the LIN bus connected. So there I'm receiving also quite a lot of RF energy. And this RF energy can then directly go into my feedback circuitry and then change somehow the behavior of my circuitry. So this is sometimes very critical when it's about the susceptibility or the immunity of ICs. So therefore, as my output driver should be used in the automotive industry, I was not using feedback controlled anymore. So I was focusing on this distributed and weighted. Okay, and this is the very, very simple, or the simplest way how a distributed and weighted structure can be done. As you can see here, the N-channel transistor, which was formerly a very big N-channel transistor, in this case was split in 3 parts. So a small one, a middle one, a big one. And also the P-channel transistor is split in a small one, a middle one, a big one. The first pair is connected together and driven directly by the former stage. Also not directly by the core logic, but the former stage. And then by inserting some resistances in combination then with the gate capacitance, we are forming an RC circuitry. So it takes a little bit until the gate signal is propagating from the first stage to the second stage and then to the third stage. So I'm not turning all these transistors on at the same time. I'm turning the smallest one on first, and then a little bit later the middle one, and then the big one. Okay, this structure still has the problem of the Grober current, because I still have this currents there. So yeah, this was already a patent that was patented a long time ago. Okay, and this is how my circuitry, or it's not only my circuitry, I did it together with a master student, Gottfried Freis, finally looked like this was the first preliminary embodiment. As you can see, we also have here all the the N-channel transistors, and there are the P-channel transistors, and we have also distributed them and weighted them. So this is the small one, middle one, next one, bigger one, and also here small one. And every transistor here got a very small pre-driver. So these are small inverters. They are not producing that much electromagnetic emission. They are just there to drive the gate signal in order to turn the transistor on at a certain amount of time. Here all the pre-drivers are connected together and operated by a kind of ramp generating circuitry. So the ramp generating circuitry was then directly driven by the signal coming out from the core logic. So it was a rectangular signal in order to turn the outputs on, for example. And what this ramp generation circuitry does, it was ramping up this output signal then with a certain rate. And all these pre-drivers, they are designed in a way that this one turns on as the first. Yeah. Then this one as the second, third, and so on until the last pre-driver is turned on. And they are turning on when the output, also this signal here, is rising up. So at this time frame, the first pre-driver is turning on, here the second pre-driver is turning on, then this pre-driver is turning on, and so on. And this leads to the fact if I would like to switch my output signal from low to high, means I first have to turn on or turn off all the N-channel transistors. So I'm turning off the big one, then this one, then this one, then this one. And then a little bit later, I'm turning on the first P-channel transistor, so the small one. Then a little bit later, in parallel, I'm turning on this next P-channel transistor, so the little bit bigger one. Then this P-channel transistor is turned on, and then in the final stage, the last P-channel transistor is turned on. And now here comes the resistance. So the on resistance of the first P-channel transistor, as it's the smallest, is the biggest. So therefore, not that much current can flow from VDD over this P-channel transistor into the output and charge the capacitor. So this dynamic switching current is not a fully inrush current. It's limited by the on resistance of this small P-channel transistor. And then the next P-channel transistor is turned on, so I have two on resistances in parallel, so more current can flow, and this further drives the output signal to the high level. So with this very simple topology, we were able to first get rid of the Grober current, because there is this break before make structure, so no current is directly flowing from high over the two transistors to low, or from VDD to VSS. And also this dynamic switching current is smoothly stepped. Yeah, this was then this slew rate controlled output driver. Yeah, we also filed in several patents on this topology, and a very big advantage was also that the size of this output driver was exactly the same as the old-fashioned tapered output driver. So here you can see the size of the old output driver with these 4 stages. So here is the bond bed where the bond wire is connected. Here are the N-channel transistors, here are the P-channel transistors, and here are just the metal frames where all these output structures are then connected. And yeah, this is the topology then of the slew rate controlled output drivers. Again, the p-channel transistors. So in this case, all this here, the n-channel transistors. Here the n-channel transistors, there the p-channel transistors. And the whole driving circuitry with the pre-drivers, the ramp generator is all here below the metal traces. So I'm not using additional space. Okay, so we also made a test chip in order to prove that this output driver has lower electromagnetic emission than the other one. So this was our special test chip. We have 8 inputs and 8 outputs, and all 8 outputs were either in test chip A, standard output drivers, and in test chip B, the slew rate controlled output drivers. Yeah, then we made some measurements. This is the output signal that comes out of the old-fashioned output driver, and this is the output signal of the slew rate controlled output driver. You can see there is not that much ringing anymore, so we have reduced ringing quite a lot. We also have reduced this ground bouncing. I'm not sure if you're familiar with ground bouncing. But in the old one, there was a ground bounce amplitude of 1.4 volts. So this is the voltage potential shift between the ground potential of the substrate and the ground potential of the printed circuit board. So when your crowbar current and the dynamic switching current is flowing out of the substrate via the bond wire to the ground pin, and then to the ground of the printed circuit board, there is always a voltage drop along the parasitic inductance of the bond wire. I'm not super happy with this, with the part of the loop inductance that is formed by the bond wire, and also there is a voltage drop due to the resistance of this structure from the bond wire lead frame down to this. And this resistance, together with the parasitic inductance, forms a voltage drop where the internal ground potential of the microchip, the ground potential of the substrate, is jumping up and down every time I'm switching something. And this is then related to ground bouncing. So the old-fashioned chip had a ground bounce amplitude of 1.4 volt, and the new chip has a ground bounce amplitude of 150 millivolt. So significant reduction of the ground bouncing. Yeah, this is assumed function of the ringing. So we could also reduce the ringing from peak to peak from 1.8 volt to 200 millivolts. Yeah, and now we were interested in how much electromagnetic emission reduction we can get. We were designing a special test board where our IC was placed on the bottom side, and we made some DEM cell measurements. And here you can see the electromagnetic emission of the standard output driver, and here is the electromagnetic emission of the slew rate controlled output driver, also of the test chips with the standard output driver and the slew rate controlled output driver. And there is a reduction of more than 10 dB over a wide frequency range. So yes, emission fulfilled, emission reduced. Yeah, we were also interested in how much reduction we can get when we are designing a printed circuit board. We designed a very, from the EMC perspective, a very stupid printed circuit board with a big loop area to generate a lot of electromagnetic emission out of this loop area. So this is our IC under test, and we were driving 8 signal lines to a load, and then the signal return current follows this path here, and we have this big loop area where we are generating a lot of electromagnetic emission out of this loop. Yeah, and we used the standard output driver test chip and the other one with the slew rate controlled test chip, and we could see that over a wide frequency range, the emission was reduced by up to 25 dB. Okay, so the output driver is very important, and if you have to design an IC, don't just use the standard output driver that is provided in the library. Check if the library is providing also some EMC improved output drivers. Some companies have some EMC improved output drivers, and some output drivers also gives you the ability to digitally control the output signal. Also, I've not mentioned it. Let's go back to this topology. So this ramp generator, this was also digitally controlled with 2 pins, also with 2 bits. And I can also change the rise time of this ramp. And when I'm changing the rise time of the ramp, I'm changing how fast these pre-drivers are turning on and turning off. And therefore, I can change the slew rate of the output signal